You ever look up at a giant skyscraper or a huge bridge and just wonder, how? How on earth do they hold all that weight up without just crumbling? Well, the answer is this really cool, beautiful principle in physics called pure bending. And believe it or not, it's the secret sauce behind some of the strongest shapes you see every single day. So let's dive in and figure this out.
Okay, so we're going to kick things off with a piece of engineering that's, well, it's everywhere. It's super common, but it's also incredibly clever. I guarantee you've seen it 1,000 times, even if you never really noticed it.
Right? Think about it. Why an eye? Why not just a big, solid square beam? Or a round one? Why this specific shape? It almost looks like it's just for style, but nope. It is one of the most critical design choices in all of construction.
And it doesn't matter what you call it, an S-beam, a W-beam, that eye shape is no accident. It's a totally deliberate, absolutely brilliant solution to a really fundamental problem. And to really get it, we need to go inside. We need to see what's actually happening inside a beam when you start to bend it.
All right, time to peel back the layers and get into the physics of it. Because here's the thing, to understand the I-beam, we first have to understand what's going on inside any beam, literally any beam at all, when it starts to bend.
Okay, so let's just imagine this simple rectangular beam. Pretty straightforward. Now, we start applying some force, we're trying to bend it. Before anything happens, it's just, a boring block of material. But the second it starts to curve, that's when things get really interesting inside.
Just look at what's happening with those grid lines. See that? The lines on top are getting all squeezed together, and the ones on the bottom are getting stretched way out. And this is key. It's not just happening on the surface. This is going on all the way through the beam.
So this is the really crucial part. The top of the beam is in what we call compression. Its atoms are literally being squished closer together. At the exact same time, the bottom of the beam is in tension. Its atoms are being pulled apart. You've got these two opposite forces, basically at war with each other, all inside this one solid thing.
Okay, so you've got this tug of war, right? Squeezing on top, stretching on the bottom. Well, this whole situation creates a really, really interesting zone right smack in the middle of the beam.
Just think about it for a second. If you're going from a state of being squished to a state of being stretched, somewhere in between, you have to pass through a point where you're doing neither, right? There has to be a middle ground, a point of perfect balance.
And that middle ground has a name. Engineers call it the neutral axis, and it's exactly what it sounds like. It's a line, or a plane, running right through the beam where there's zero stress and zero strain. Nothing. While the top and bottom are doing all this heavy lifting, the middle is just kind of chilling. It's just along for the ride.
And wow, this image shows it perfectly. This is a computer simulation of all that stress. That bright red at the bottom, that's maximum tension, where it's being pulled apart the most. The dark blue at the top, maximum compression, squished as tight as it can be. But look at that big green zone in the middle. That's our neutral axis. That's the zone of nothing. It's experiencing almost no stress at all.
Okay, so this is where it all starts to click. This brings us right back to our original mystery. If the middle of the beam is basically doing nothing, why do we even have material there in the first place?
Now, check out how this diagram maps out the stress. It's not like it just suddenly appears. See the arrows? The stress starts at zero, right at that neutral line, and then it grows. It gets bigger and bigger the farther you get from the middle. All the real work, all the heavy lifting, is happening at the very top and very bottom edges.
And there it is. That's the aha moment. Just look. Compare the stress diagram on the left to the I-beam on the right. It's the same shape. They're practically identical. The I-beam is basically just a physical model of that stress diagram. It is pure genius. You put the material where the stress is highest, at the top and bottom, and you just carve out all that lazy, useless material in the middle that isn't doing anything anyway.
And this is why it's such a game changer. By getting rid of that material that's not doing any work, you get a beam that is almost as strong as a solid rectangle, but it weighs a whole lot less. And that saves a ton of material, a ton of money, and makes the entire building or bridge lighter and way more efficient. It's a win-win-win. Here's another great way to picture it. Look at these two beams. They are made with the exact same amount of material. They have the same area, but the one on the right, the taller one, is way, way stronger when you try to bend it. Why? Simple. More of its material is pushed farther away from that lazy neutral axis. So it's not just about how much stuff you have, it's about where you put it.
Now, of course, engineers aren't just winging it, right? They don't just eyeball this.
They have taken this really elegant, intuitive idea and turned it into a precise set of rules, into math, that lets them design and build these massive structures with total confidence.
It really boils down to two key numbers. First, there's the moment of inertia, which we just call I. That's all about the shape, how you've arranged the material. The other one is the section modulus, or S. You can think of S as like a grade for how good your beam is at fighting stress. The bigger your S value, the stronger your beam is. Simple as that.
In this formula right here, this is basically the secret code. This is the whole thing in a nutshell. It connects the bending force, that's M, with the strength of the material itself, E, and the strength of the shape, I. With this one little equation, an engineer can predict with incredible accuracy exactly how much a beam is going to bend. No guesswork.
And this quote really just sums it all up perfectly. A beam section with a larger section modulus will have a lower maximum stress. I mean, that's the whole game right there. Your job as an engineer is to design a shape that gives you the biggest possible section modulus using the least amount of material. And as we've seen, the I-beam is an absolute champion at doing just.
So, it turns out the big secret of the I-beam was hiding in plain sight the whole time. It's just a masterclass in efficiency. Put your strength exactly where you need it and get rid of the rest. Now that you know this principle, I promise you are going to start seeing it everywhere. So take a look around. What other everyday objects are hiding this exact same clever idea?